Think about, the last time you saw something completely baffling in the natural world. Like maybe you were walking through a park and you noticed this massive flock of birds, and they suddenly changed direction in perfect unison, like a single liquid entity. Your brain immediately, it tries to fill the void of the unknown.
Oh,
Right.
absolutely. It's human nature.
Right. So you might think, I don't know, oh, they're following a leader, or they're just reacting to the wind. We are biologically wired to make these rapid-fire guesses to make sense of our surroundings. But in the realm of science, a quick guess, even if it's a highly educated one, is never enough.
No, it's not. I mean, it's really the difference between human intuition and rigorous investigation. Because intuition tells you, well, the sun revolves around the earth, right? Because you watch it move across the sky every single day. But investigation requires you to stop, look at the underlying mechanisms, and actually prove what is happening.
Which brings us to our topic today. Welcome everyone to today's deep dive. Whether you are a student, a parent, an administrator, or an educator, we are exploring the architectural blueprint of how we teach young minds to stop guessing and start investigating. Today's mission is all about unpacking a core piece of the 7th grade life science curriculum, specifically Bioforge 1.1.6, constructing explanations and designing solutions.
And this specific practice is, honestly, it's the beating heart of a life science course. It's that pivotal moment where students stop just, passively absorbing textbook facts and officially step into the role of apprentice scientists. They're tasked with answering what is arguably the most profound scientific question we can ask, which is, what is happening and how do we know?
Right, how do we know? That's the kicker. And to get us all in the right headspace for this, I want you to imagine a very specific mental workspace. This is kind of the visual language of the Bioforge curriculum. Picture this expansive, striking orchid plum-colored design table right in the center of a room.
It's a great visual.
Yeah, and over on the walls there are these detailed blueprints pinned up full of annotations. There's this focused, sharp beam of light illuminating a complex diagram on the desk, and right beside it, you have heavy metal gears turning rhythmically next to, like a delicate green sprouting plant.
I love that imagery because it's a space that perfectly represents the intersection of the natural living world and deliberate human innovation. That table is the workbench where raw confusion is actively transformed into clear, defensible explanations, using actual evidence.
So let's start with that first concept, constructing explanations. Because in everyday life, if somebody asks me to explain why I was late to a meeting, I am essentially just offering an excuse, like I lost my keys or traffic was bad. But constructing an explanation in the 7th grade science lab, that carries a vastly different meaning.
A completely different meaning, yeah. In plain language, constructing a scientific explanation means moving beyond just noticing a phenomenon. It is the deliberate act of connecting a specific real-world event to the invisible underlying scientific mechanisms that caused it.
So it's not just a recap.
Exactly. You aren't just summarizing what occurred. You're laying out the precise chain of causality. You have to answer the how and the why.
And navigating that distinction, that can be incredibly messy for a 12-year-old. They communicate constantly in their daily lives, but they are rarely asked to scientifically explain something. Yeah. And the framework we're looking at draws some very hard boundaries between an explanation, a description, an opinion, and just a guess.
Right. Separating those four categories is actually the first major cognitive hurdle in the classroom. Let's ground this in biology for a second. Imagine a class looking at red blood cells under a microscope. An opinion is entirely subjective. It's driven by emotion or preference. So a student might say, red blood cells are the most fascinating cells in the human body.
Which is a lovely sentiment, but it offers zero scientific utility.
None at all. So then we have a description. And a description is just a report of sensory input. Red blood cells look like tiny red donuts.
Which is true.
It is factually accurate, yeah. It tells us what the object looks like or feels or behaves like, but it focuses purely on observable surface-level traits.
So it's kind of the equivalent of me describing a sports car by saying it has 4 wheels, it's painted bright red, and it makes a loud noise. Like, I've described the car, but if you ask me how it actually propels itself forward at 100 miles an hour, my description is totally useless.
That is a perfect analogy. And that brings us to the guess, or what we'd call an isolated claim. A student might say, red blood cells move oxygen around the body. Now, that is a true statement, but if they offer no proof or reasoning attached to it, it's functionally just a guess.
Because they could have just heard it on a TV show or something.
Exactly. They might have heard it somewhere, but they can't defend it. They don't know why it's true.
So to turn that into a true scientific explanation, going back to the car analogy, we have to metaphorically lift the hood. I can't just tell you the car is fast. I have to show you internal combustion. Like, I have to explain how the fuel injector sprays gas, how the spark plug ignites it, the piston driving the crankshaft, and how that kinetic energy turns the axle. I have to, like, reveal the hidden mechanism.
Yes. And returning to our blood cell, the scientific explanation would sound something like this. The biconcave, or donut-like shape of the red blood cell, increases its surface area, which allows oxygen molecules to diffuse rapidly across the cell membrane for efficient transport through the capillaries.
Oh, wow. Yeah, that's a huge leap from they look like red donuts.
It is. You have synthesized the observable fact, the shape, with the underlying scientific principle of diffusion.
But here's my question, though. Why is there such a magnetic pull for students to default to just descriptions? Because honestly, even adults do this. We're asked to explain something, and we just describe it in increasing detail.
Well, it really comes down to cognitive load. Describing requires very little of your brain's processing power. You're acting as a simple conduit, just reporting what your eyes or ears are taking in. But explaining requires you to synthesize empirical evidence with theoretical principles.
That's a heavy lift.
It's massive. You have to take the visible world and map it onto the invisible laws of nature. That forces a huge cognitive reorganization. It's mentally exhausting.
Which means we can't exactly just drop a complex biological phenomenon in front of a middle schooler, tell them to synthesize empirical evidence with theoretical principles, and expect them to succeed. I mean, they need scaffolding, right?
Absolutely. They need a neurocognitive map to manage that tax on their brain. And the gold standard for that is the CER framework: claim, evidence, and reasoning.
Let's pull this framework apart because I feel like CER is often misunderstood as just like a formatting trick for writing a paragraph. But looking at the mechanics of it, it's actually a system for forcing the brain to slow down.
That's exactly what it is. So the first component is the claim. It's a concise, declarative statement that directly answers the scientific question. It's the conclusion the student has reached. But making a valid claim requires a cognitive function called inhibitory control.
Inhibitory control. So that's the brain's braking system, basically.
Yes. The student has to physically suppress the urge to just blurt out their gut reaction or a random guess. They have to pause, evaluate, and formulate an objective statement.
Okay, that makes sense.
Then they move to the second pillar, which is evidence. This is the scientific data that supports the claim. And this is where we have to be incredibly rigorous, because evidence cannot be a hunch. It must be appropriate, and it must be sufficient.
And let's step outside the classroom for a second to illustrate why empirical evidence is so vital. Because this isn't just an academic exercise. I mean, consider people making survival decisions in the Alaskan wilderness. When they're predicting a sudden weather shift, or tracking the migratory path of caribou, or assessing whether a frozen river is safe to cross, they do not rely on guesses or opinions. Their lives literally depend on recognizing patterns of empirical, observable data in the natural world. They're constantly filtering out irrelevant noise to focus on the specific data points that keep them alive.
That is the perfect real-world application. It grounds our claims in reality. And for a student sitting in a classroom, selecting the right evidence demands intense working memory. I mean, if they're looking at a complex chart showing predator and prey populations over 20 years, they have to hold their specific claim in their mind while sorting through all that data, trying to isolate the exact numbers that prove their point.
That sounds incredibly draining, which leaves us with the final, and I think notoriously most difficult piece of the puzzle, the R reasoning. This is kind of the logical glue that binds the evidence to the claim.
It is. Reasoning is the justification. It requires the student to explain why their data counts as evidence by applying underlying scientific theories. Because if a student only lists observations, they're just a recording device. Reasoning forces them to argue why the data matters.
I often think of reasoning like a lawyer in a courtroom. The lawyer can't just, drop a bloody glove on the judge's desk and walk away.
Right, they'd lose the case immediately.
Exactly. The glove is the evidence, sure. But the lawyer has to provide the reasoning. They have to explain the chain of custody, the DNA analysis, and how the glove definitively ties the suspect to the crime scene.
And doing that requires metacognition.
Which is thinking about thinking, right?
Literally the act of thinking about your own thinking. Cognition is doing the math problem. Metacognition is floating above yourself, asking, wait, did I use the right formula here? The student has to step outside of their own argument and ask, does this make logical sense? Am I relying on the laws of biology to prove my point, or am I just repeating my data? Translating that complex internal logic into formal text is a colossal developmental leap for a young mind.
Okay, so once our apprentice scientist has successfully played the lawyer, gathered the empirical evidence, and constructed a rock-solid explanation for why, let's say, a particular ecosystem is collapsing, the natural human impulse is to ask, well, how do we fix it? Which transitions us seamlessly into the second half of this practice, designing solutions.
All right, because if the first half is about understanding the world, the second half is about intervening in it. Designing solutions is the systematic process of solving human problems by creating a physical object, a tool, a process, or a system that balances competing demands.
I have to admit, when I hear the phrase middle school design project, my brain immediately conjures up an image of popsicle sticks, hot glue guns, glitter everywhere, and just a total lack of scientific rigor, just a chaotic arts and crafts session.
You are definitely not alone in that. And you're identifying one of the most common pitfalls in science education, which is treating engineering as an unguided maker day. There is a hard, very serious line between a craft project and a true, rigorous engineering solution.
Let's use the bird nest example because it perfectly illustrates this trap. Say the class is given a habitat design challenge. If a student gets a pile of feathers, mud, and glue, and they spend 2 hours building this visually stunning, intricate bird nest, but they never take a single measurement or test its durability, that's a craft.
Yes, it is. It relies entirely on intuition and aesthetics. It's just trial and error without a scientific compass.
So what's the alternative?
True engineering requires that science is the limiting factor. The constraints must govern the design. So a true engineering challenge for that same bird nest would sound like this. You must build a nest that maintains an internal temperature of 20 degrees Celsius for 5 minutes while sitting directly on a block of ice.
Oh, wow. Okay.
Furthermore, it must weigh under 50 grams, and you have a strict budget of points to spend on materials.
See, as someone who would have definitely built the sparkly, useless nest in middle school, I look at those constraints and immediately feel boxed in. Doesn't our heavily restricting the materials and adding all these rigid rules just squash the creativity out of the process?
It seems counterintuitive, I know, but constraints are actually the engine of creativity. When you have unlimited resources, you don't really have to think deeply. If a design doesn't work, you just add more glue. But when you only have 50 grams of material to insulate against solid ice, you are forced into trade-off analysis.
Let's play that out. So, if I'm the student, my first thought is to wrap the whole nest in something thick and heavy, like clay, to block the cold. But clay is incredibly heavy. I would immediately violate the 50-gram weight limit.
Exactly. You hit a constraint, so you have to pivot. What if you use cotton balls instead? They are incredibly light.
Right, but cotton absorbs water, so the ice block is going to melt slightly, the cotton will soak it up, and the inside of the nest is going to drop well below 20 degrees Celsius.
And right there, in that realization, you are doing real engineering. You are balancing competing demands. You have to rely on your scientific knowledge of thermal energy transfer and material properties to optimize the design. You realize you need a waterproof barrier on the bottom, maybe a thin layer of wax paper topped with a lightweight insulator. The creativity comes from navigating those restrictions.
So we have these two immense cognitively heavy tools. The ability to deconstruct and explain natural phenomena using claim, evidence, and reasoning, and then the ability to solve problems using rigid engineering constraints and trade-off analysis. How does this actually map onto the 7th grade life science curriculum? Because we aren't just doing this in a vacuum.
No, not at all. This specific practice is woven into almost every major unit. Students use this explanatory framework to model how individual cells function and how specialized body systems interact to keep an organism alive. They map the complex transfer of energy during photosynthesis, for instance.
And it scales up to macro-level issues too, right? I know they use these tools to analyze massive ecosystem disruptions, trace the causes of biodiversity loss, unpack the mechanisms of natural selection, and design literal solutions to mitigate negative human impacts on the environment.
They do, yeah. It's incredibly comprehensive.
But I keep coming back to the mental tax of all this. We are asking 12-year-olds to perform trade-off analysis on global biodiversity loss using working memory and metacognition. That sounds like a recipe for a massive spike in student anxiety. How does the curriculum ensure that a diverse classroom of learners doesn't just, drown in all that complexity?
That is exactly where Universal Design for Learning, or UDL, becomes the safety net. because UDL isn't just about watering down the content. It's about removing the unnecessary barriers to accessing that rigorous content.
Let's talk about the specific scaffolds, because they are fascinating from a neurological standpoint. Take sentence frames, for example.
Yeah, a sentence frame provides the structural syntax for an argument, like I claim that X is true because of Y evidence. By providing that frame, we eliminate the cognitive burden of trying to remember how to structure a paragraph. So the student's working memory is freed up to focus entirely on the science concepts.
And they also heavily utilize physical models and visual diagrams, right?
Yeah.
If a student struggles to hold abstract data in their mind, giving them a tangible model anchors their thinking.
Absolutely. And the inclusion of oral explanations is huge as well. Think about a student who is a brilliant observer of the natural world, who understands the mechanisms perfectly, but who suffers from severe dysgraphia or writing anxiety. Allowing them to orally present their CER means we are assessing their scientific knowledge, not their handwriting.
That's so important.
It really is. The curriculum also uses checklists to help students track those engineering constraints, breaking a massive problem down into manageable cognitive chunks. But honestly, the most vital support system built into this entire framework is the use of iterative revision cycles.
Let's camp out on revision cycles for a moment, because there is a profound psychological shift that happens here. Think about the student who suffers from crippling perfectionism, the one who will stare at a blank page for 20 minutes because they are just terrified of writing the wrong answer. When you integrate revision cycles into the core DNA of the classroom, you are explicitly teaching them that their first attempt is not expected to be perfect.
It completely shatters the illusion that science is about instantaneous brilliance. Professional scientists and engineers fully expect their first prototypes to fail. When students realize that failure isn't a permanent grade, but rather a necessary data point for the next iteration, the anxiety just dissipates.
It transforms the classroom culture. The goal is no longer flawless performance. The goal is progression based on feedback. If your ice block bird nest drops to 15 degrees, you don't fail the class. You analyze the thermal failure, you trade out your materials, and you build a better one. It builds this immense, resilient academic confidence.
It really does. And that brings us full circle to that visual metaphor of the Bioforge workspace. The blueprints, the gears, the design table, it shifts the entire dynamic of education. It moves the classroom away from simply doing activities to pass the time and transforms it into a laboratory where students are authentically figuring out the complexities of the natural world.
Which brings our deep dive to a close. We have journeyed from the anatomy of a true explanation, through the rigorous cognitive demands of evidence and reasoning, all the way to the liberating creative power of engineering constraints in life science.
It is a remarkable cognitive evolution for a student to undergo.
It really is. We often fall into the trap of thinking about science as just an encyclopedia of static facts that we force kids to memorize for a test. But science is not just knowing facts. Science is learning how to explain the world and design better ways to live in it.
Beautifully said.
And we want to leave you, our listener, with a final thought to mull over. If we successfully trained an entire generation of middle schoolers to pause, suppress their initial emotional guesses, demand empirical evidence, and rigorously analyze trade-offs before proposing a solution, how might that change the landscape of our adult society? Imagine what our social discourse, our civic debates, and our problem-solving could look like if we all operated like apprentice scientists. Thank you for joining us on this deep dive.